Okay, this is the last of our series of videos on neural networks, and in fact the last of our series of videos on machine learning, and we'll be talking about practical issues in designing neural networks. So we mentioned in the previous video that there are three stages to implementing neural networks. The first stage is loosely connecting the components. Now that's what we're going to talk about here. How do you provide these preliminary connections, the preliminary configuration for backpropagation to work on? So that's what we'll be talking about in this video. Right. From the previous discussion, there are four key aspects to consider when designing a neural network. First, you have to design the input nodes, then you have to design the output nodes, and then you need to choose a loss function, and then you need to design the interior layers. This includes both the nodes and something we haven't really talked about. Previously, we've had all the nodes connected at each layer, but in fact, you can choose which nodes to connect. You may not include all of the connections. And you may have heard about convolutional neural networks, and that's what those are all about. You don't use all of the connections between all of the nodes of one layer and the next layer, but you selectively choose some to reflect the structure of the data. So we won't talk more about that, but that's really the basic idea of convolutional neural networks. So here we are showing all the connections, but that's a design decision. Right? So designing the input nodes, we've talked about this before. These come from the data sets. You have to decide which features, or whether to change the features, produce more features, make combined features to give to the neural network. So that's your decision. Now each characteristic or each feature will have its own input node, and you have to decide which ones you're going to use. I mean, if you're talking about financial issues, you're probably not going to be including eye color. So you have to make that intelligent decision of which input features to include, and then you assign them to nodes. And of course you have the one node that's just the constant feature. Now, what about images? Well, images consists of pixels. In this image at low resolution, you can see the separate pixels which look like squares. Now, each pixel typically corresponds to a level between 0 and 255. So you may wonder, why 255? Well, if you have from 0 to 255, that's 256 levels. And 256 is 2 to the 8th power. So in fact, you can use 8 bits to store one pixel. And if you're not familiar with the concept of bits, don't worry about it. This is a practical issue that relates to computers. So you can see here that we've put a value on each pixel, and you can see the low values correspond to darker pixels, and the high values correspond to lighter pixels. Now you take these numbers, and this is going to provide your inputs. Here you have 16 pixels by 22 pixels, and you can arrange them row by row and flatten them into a single row. So the first row will be the first 16 pixels, second row is second 16 pixels, and so on. And these can be your inputs. A lot of inputs, 352 inputs. Now, just as an aside, the networks that we've been looking at, you connect every one of these pixels, or any one of these inputs rather, to all of the nodes in the next layer. But for a convolutional neural network, you wouldn't do that. You would only connect, say, these 4 pixels here to one node in the next layer, because you want to look at features that are local that relate to small areas of the neural net of the image, and build that up to more and more complex features. So, if you're interested, there are many, many references about convolutional neural networks. Right, so that's the input nodes. Output nodes are selected so that they match the desired output. Right? So of course, if you have binary classification, you only need a single node with sigmoid activation function, just like logistic regression. Now it's worth re-emphasizing that the difference between logistic regression and neural networks, in logistic regression, if you want to have a complicated boundary between features, you have to supply the polynomial features or compound features to make the logistic regression work. But in neural networks, the neural network itself will create those complex features for you. So the neural network saves you the effort of figuring out how to combine features into complex features. Now, in the case of multi-class classification, we saw that instead of one output, you'll want several outputs. You want one output for each class. And you use one-hot encoding to identify the different classes. So you can review that in our previous video. Right. So we could use n output nodes with a sigmoid activation function for each output node. This was because we were trying to show how multi-class is just a generalization of binary classification. However, there's a better way to do this when you have multiple classes. In this case, if you have a sigmoid activation function for each node separately, then the outputs are not going to add up to 1. So you're not going to get a probability distribution. It's better if you arrange with a softmax activation, which guarantees that all the outputs, when summed, will give you a 1. So you're going to be outputting a probability distribution. And now you want to compare that with your one-hot encoding. And there's a standard way of doing that called categorical cross-entropy, which is also called Kullback-Leibler divergence in mathematics books. And it's a standard way of comparing two probability distributions and finding the difference or distance between them. So for multi-class classification, the natural way, mathematically speaking, is to use softmax with categorical cross-entropy, which, as I said, gives you a probability distribution on the outputs. Now, on the other hand, you might have a situation where multiple classes can be correct, like an object could be an animal and a mammal and a dog. I think this is a more unusual case, but if you did have such a case, then you would want to evaluate each alternative separately, right? You want to decide animal and not animal, that's independent of whether it's mammal and not mammal, and dog is not dog. You'd want to make these determinations independently. So you would treat each node as a binary classification, and you'd use binary cross-entropy for each node, each output node. Now, so far in our discussion of neural networks, we've been emphasizing classification and the connection between neural networks and logistic regression. But in fact, neural networks can do prediction and improve on the performance of linear regression. And there's a similar relationship. In linear regression, if you want to have a more complicated prediction, you need to create complex features. However, the neural network can take your simple inputs, your simple features, and create complex features for you. So the neural network does the work. Right? So instead of having a output that ranges from 0 to 1, we simply have an output that ranges from minus infinity to infinity. If you're predicting a real valued quantity, like days to sell a house, which may not be between 0 and 1, or price or profit or something like this. So you want to have a continuous output. In this case, your output node would have no activation function. You just simply let the outputs range freely. So this is called a linear activation function. And for the loss function, we would use the same loss function as for linear regression, mean squared error. You can also use mean absolute error or root mean squared error. Of course, mean squared error is mathematically easier to deal with. So just to show how you would use a neural network for prediction instead of classification, in fact, there really is no difference at all except at the very final layer. You still have a similar structure as before. You still have the nodes in the hidden layers depending on the nodes in the previous layer. Linear combination of the nodes in the previous layer using the weights. Then nonlinear activation function. Right? So I get all of the nodes in this layer, in the second layer, in the same way. Then I go on to the third layer. Similarly, linear combination of the nodes in the second layer. Apply activation function. Do that for all the nodes in the third layer. And of course, we're adding a constant feature at each layer. Then finally, you have your final output, A4. Linear combination of the nodes in this layer. However, at this layer, you simply take the result and don't apply an activation function. So that will enable you to have a range of numbers that's not just between 0 and 1. And we take as our cost function just the same cost function we had before. The h is now just going to be the final output. So just to summarize, with linear regression or prediction, you're going to take one output node, if you're predicting one quantity with no activation function, and you can use mean squared error or some other similar loss function. Okay. Now, we can also do regression of multiple values. For instance, an image with n pixels. Now, the difference here between image with pixels and, say, the price of a house is we know that for an image with n pixels, each pixel value is going to be between 0 and 255. So you could just create one output node for each pixel and use the same linear regression scheme that we talked about in the previous slide. But it's probably better to have a sigmoid activation function that will guarantee that your output's between 0 and 1. And then you just scale up. You just multiply your result by 255 to give you the correct pixel value or the predicted pixel value. Now you'd use binary cross entropy because each pixel is being evaluated independently of the others. Now, as far as interior layers and nodes, there are no strict rules. And this comes more with experience and also can depend on your particular application. So the general idea is that the more nodes and the more layers, the more complexity you will have. Now, it is possible to have a very complex neural network solve a relatively simple task, but then you should make sure to use regularization. And as far as number of hidden layers, you can evaluate different possibilities just like you evaluate different models. You compare the performance, you train each model on the training set, you evaluate on a validation set and pick the best. This is just the standard procedure for comparing different machine learning algorithms. And indeed, you can compare neural networks with other machine learning algorithms in the same way. So here are some rules of thumb. For most data sets that are not really large, 1 or 2 hidden layers are more than sufficient. But for more complex problems like time series and image prediction, more layers certainly helps a lot. And the size of the data set makes a big difference. If you have a very big data set, then you really are not able to train a neural network with lots and lots of layers and lots of nodes. But for small and medium-sized data sets, probably 1 or 2 layers, hidden layers will be enough. And for large data sets with more than 1 million samples, more hidden layers may be useful. Now, a lot of people use very complicated neural networks with lots of layers for small and medium-sized data sets. I think all too often people do this just to appear impressive. It's really not doing much, but if you use regularization techniques, it's not going to hurt you. And neural networks are very forgiving, just like the human brain. You can use the human brain to solve very simple tasks. Like, for instance, telling whether a traffic light is green or red. Human brains can do that, but you could also make a very simple circuit to do the same thing. Now let's consider activation functions. Until now we use the sigmoid function on hidden layers. But in practice this is not used because the gradient is expensive to compute. And also out here towards the edges, the gradient vanishes, so your neural network won't train. If you're way out here, then gradient descent is not going to take you very far, very fast. Hyperbolic tangent is a little bit better, but this also has a gradient that's expensive to compute. One that's commonly used is the ReLU function, which you can see. It's flat for negative values, and then it's just the regular y equals x function for positive values. It's a good option for hidden nodes. It's not used for output nodes because it limits the output. The gradient is very cheap to compute, and it also has a large range. Now, one issue is that when z is less than 0, learning stops because gradient descent is not going to be able to determine which direction to go. So an alternative that will solve that problem is the leaky ReLU unit, which has a small gradient for negative values. Okay, so this is a very good option for hidden nodes when the ReLU fails, especially in deep networks. Again, not used for output nodes. The gradient is still very cheap to compute. The main issue is there are more hyperparameters, but that's really not a big issue. You just choose some small gradient here. And the size of the gradient probably will not have that much influence on the performance of the neural network. Now, there are other techniques for regularization. And as I said, regularization is quite important because you can use an over-complex network to solve a simple problem, but you would certainly need some techniques for making sure that you're not overfitting. One way to do this is something called dropout, where instead of using all the nodes all the time on all the instances, you randomly switch off different nodes at different times. So what this does is it builds some robustness into the network. So the network has multiple ways of determining the correct result. Now, this idea of creating multiple ways is quite common in machine learning and comes because you have a lot of computing power so that you can build in this kind of redundancy. Another example of a similar technique is random forest, where you use not just one decision tree, but lots of decision trees to determine a result. And the different decision trees balance each other out. So the same thing is working here. you're getting these different determinations balancing each other out so that the neural network doesn't depend too heavily on a single pathway. All right, so that's a taste of neural networks, and there's certainly a lot more to the topic, but I hope you've gotten a good introduction. Thanks for watching.